Welcome to another exciting Java class. In this class we're going to look at Brian's solution to the shortest path problem. What algorithm did you use, Brian?
You referred to a Stack Overflow question, and I used the answer.
Did you use Dijkstra's algorithm, Prem's algorithm, depth first algorithm, breadth first algorithm?
It was a recursive algorithm.
You used the recursive depth first algorithm? I'm not hearing a yes. What'd you use?
I think it was
Breadth first? Well, Dijkstra's algorithm is a breadth first algorithm.
It was that one that you showed up.
I don't know if you guys are, well, here's the deal, okay? And I just talked to Mary Kleps about this. Turns out that Blackboard doesn't send you an update when I change the assignment to add hints, which really pisses me off, because I would like people to see the updates as I post them to the assignment, and I think you would like to see them too. According to Mary Kleps, the only way for you to see them is for you to change your preferences. She tells me, well, those preferences are up to the user and I have no control over them, and they're user preferences. I said the defaults should be something I can set, and she says, no, the user sets the defaults. And I said, no, they don't. The defaults are being set by the manufacturer of Blackboard. And the manufacturer of Blackboard has set the defaults so that when I update an assignment, you don't get to find out about it. That's the default. I don't think that's a reasonable default. I'm very sorry for that. So in the future, after I update an assignment with hints, apparently, I also have to send out an announcement. That's part of the workflow. And then I have to mark the announcement as an email, which gets sent to the people. There's a compelling argument against changing learning management systems without any consultation with the faculty, which is what we have done apparently when we abandoned IDOS in favor of Blackboard. I can't think of anything nice to say about that procedure, and so I won't say anything at all, because that's what my mother told me. So here's the deal. If you went to course content and you looked at the latest updates in Homework 3, what you would have seen is a whole pile of URLs. Did anybody notice those URLs? One person out of the whole class. Well, I'd like to say that that really pisses me off, but for some reason it doesn't. I don't know why. It probably should. So here's the deal. All of these algorithms, flood fill, Prim's algorithm, Dijkstra's algorithm, they're all different approaches to the same exact problem. Well, let that be a lesson to you. There's more than one way to skin a cat. Turns out, when you're searching a maze, it's the moral equivalent, computationally, of searching a graph. And when you search a graph, there are two kinds of searches. Okay? Breadth first search and depth first search. Okay? In breadth first search, you search each layer, and then you go to the next layer, and you keep track of the costs at each layer. Breadth first search is just like Dijkstra's algorithm, where Dijkstra's algorithm tries to keep track of the costs of getting to a specific node by using some sort of a data structure, maybe a stack, in order to be able to determine what the shortest way is to a given node. Turns out the direct link to a given node may not be the shortest. You may have to go around a corner in order to get to that node, especially if there's something in the way, like a wall. So if you think about depth first, that's quite different. With depth first, you go all the way down, hugging, let's say, the left side of the tree until you get to a leaf node. Keep track of the costs all the way, and then you go down all the way to just before that end leaf node, and you go the other way. and then you go all the way down to just before the parent of the branch prior to the two leaf nodes, and you go another way. So you try iteratively all possible routes until you get to a place where you can find the costs, all possible costs to a given endpoint. That's depth first search. With flood fill algorithm, you have very close to a breadth first search. And what you're doing with flood fill is you start with a seed node, and then you spread out to all adjacent nodes. And as you go to those adjacent nodes, you put into those adjacent nodes the costs of getting there, which in our case will be the number of hops. And then you go to the next adjacent nodes. That's breadth first, flood fill. Flood fill algorithms are very good if you have something that looks like a bucket in a paint program, and you click on some pixel, and all of the pixels with the same color all get the color of the palette that was selected prior to clicking with the paint bucket. There's a program, Windows has this. I think it's called Paint, isn't it? Yeah, the Paint program has, I'm thinking a bucket. Is that a brush shape? No. Yeah, there it is. There's the bucket. So then if you pick a color, here's a color red, and then you click on the bucket, it fills everything with red because all the pixels are adjacent. So you're exploring all the adjacent pixels. Picture a maze where instead of having adjacent pixels, you might have areas that are isolated by, let's pick a brush. Something like that. That isolates the area. Now if you pick a flood fill with a bucket and you flood fill that area gets filled. That's a flood fill right there. So now if you're trying to do a maze search and you're trying to get costs, those flood fill costs will be reflected in the distance away from the source. So what I'm thinking here is if you're trying to do a maze algorithm where you're finding a shortest path, you could start by using a flood fill algorithm and use your distance in terms of the number of hops, and take that distance and put it in to the actual character that's being used for storing the two-dimensional array. If you do that, then you've got a cost as you go in a breadth first search toward your destination. And so by having those costs in there, it's computationally equivalent to building a graph that's not directed and gives you costs for each edge. And so that's key. It's a way to approach the problem that allows you to leverage the existence of the two-dimensional array that you've already got for representing the maze. That way you don't have to represent what I would call a parallel data structure for your graph. Because if you went to your standard Dijkstra algorithm, what they're doing is they're using vertices and edges in a graph data structure. And that's typical. But now you've got two data structures. You've got the maze, which is a two-dimensional array, and then you've got the graph, which is a whole other data structure. And in this case, I'd like to be able to combine the two. I did the same thing for Chapter 12 in the Martelli algorithm, where I used what's called an edge element. So if you go to Martelli algorithm and you look at the so-called A-star algorithm for computing the boundaries around areas for a smart scissors, what I do is I have you click on 2 points in pixel space, and then I search through the pixel space in order to find the best edge. And that effectively is what you guys might do if you were going to use the image to do the proper solution to the maze. But if you just want to use the maze data structure that was given, this flood fill algorithm might be a nice way to go. So lots of different algorithms available to you. And Brian says he has a solution.
Yeah, I made it easier. I sent a screencast.
You sent it as a screencast?
Yeah,
That sounds very fancy. Grade center needs grading. Let's look at Brian's graded homework. Is there a way to just look at your solution? Sorry for my lack of facility here. New tab, paste, enter. Jing. Oh wow, you're using Jing. I only recently learned about that. Now, is there a way to make that fill the screen?
If you're going to watch, I'd focus in on the top left corner because that's where the maze will be generated.
Okay, let's do that. And you didn't narrate this because it's silent.
Yeah, it's silent. But I step through the code a little bit. It's not long. I just
Oops.
browse it and then I run it.
Am I in the right place here?
Yeah. It'll come up.
Oh, that looks cool.
So I do it again just to show. Yeah, that's it.
Now, was that a depth first search or a breadth first search? That looks an awful lot like the Sedgwick search.
It seems like a depth.
Yeah, I think we've seen that before. Let me see if I can figure out whether or not I have this one. But it didn't actually use any of the image generation that I had provided as
I
the
just changed it to
ovals.
I used your code and I modified it to run my maze solve. And then I just made it oval because I like that look.
So here is a depth first search. And that finds an answer.
Yeah, mine's a depth first.
Let's see if I can do another one. Here's one where we look at the left-hand side of the edge. That's the one we started with. Here we're just hugging the left corner until we find an answer. But that's not necessarily a shortest path. It's just a solution. Let's see. Maze to image. I think this is the one. Right. That's also just hugging the edge until you find an answer. But of course, it's not a shortest path, right? Because what we're doing is we're just looking at hugging the wall until we get to the end, where green is the beginning and red is the end. This one we've seen already. I'm not sure what that one's doing. Huh, that looks bad. I don't know what that's doing at all. Let me see if there's any others. This one, I started doing a conversion from a C program that Kyle and I were working on. The C program used, this is one of the URLs I sent out to the class.
That's one I used.
Is it?
Yep, I modified it a little.
Cool. I was thinking that if you used it, you would somehow create an image similar to the image that I had, because ostensibly we would want to use image processing to drive the maze solution. Maze solving is useful in image processing because it enables us to do edge detection. It lets us find a good edge through the image in the presence of noise. This is a big question for us. What's a good edge? Well, let's put it a different way. What's an edge?
Something different.
Different, yeah, something different.
Something non-homogeneous.
Is it non-homogeneous? I don't know. Homogeneous point processing, what's that?
Like the
Paint
paint fill.
fill.
The one you just
Paint fill. Paint fill is not. Paint fill is most definitely inhomogeneous image processing because it relies on prior pixels. It's searching from a given pixel to adjacent pixels. Homogeneous point processing is homogeneous because all pixels are treated the same. Edge detection looks for change in energy. And change in energy requires that you know prior pixel energy before you go to the next pixel. So homogeneous point processing is really very different from edge detection. If you wanted to take every image pixel and make the negation of that image pixel, that's homogeneous point processing. If you wanted to take every pixel and make it a little darker, that's homogeneous point processing. You want to make every pixel and change the contrast, that's homogeneous point processing. But if what you want to do is find an edge that traces from one pixel to the next pixel, because you need to know the prior pixel, it can't be considered homogeneous point processing, because now you've got two pixels that are adjacent to one another that know about each other. And if you're looking at energy going across a barrier inside of a contiguous segment or region of an image, well, clearly that can't be homogeneous point processing. So when we think about Chapter 12, which is edge detection and boundary processing, it's completely different from Chapter 4, which is homogeneous point processing. And that's not to say that homogeneous point processing isn't totally important. We need these things, right? Being able to enhance an image, improve its appearance, give it a better dynamic range. This is very important stuff, but that is considered, for no particular reason I can think of, as low-level image processing because it doesn't consider adjacent pixels. Each pixel is held on to itself by itself without consideration of adjacent pixels. That's homogeneous point processing. So edge detection in general is not homogeneous point processing. Not generally. And so that brings us to, well, some of the big questions. What's an edge? It's a sudden change in energy. That's what low-level edge detection would tell us as we go across a segment. And then the bigger question is, what's a good edge? That's a big question, right? Because what you see as a good edge, because of your knowledge about what edges are and what good edges are, is really different than what the computer sees. And for you to take that knowledge and put it into a computer algorithm that recognizes good edges is a challenge. And the reason why it's a challenge is because you have to communicate knowledge to the computer and to the computer algorithm, which means you have to represent that knowledge. And then the question becomes, how do you represent the knowledge about what a good edge is? And I'll give you an example. I could have a great edge in terms of change of energy from a shadow because it goes from light to dark, and there's a lot of energy change. But that shadow has no architectural relevance. That shadow is not part of the building. That shadow is not part of the tree. Right? The shadow has no geometric representation at all. We don't think it's a good edge. It's just a shadow. But The computer says it's a good edge, and you say because of your knowledge about architecture, it's not a good edge. Why? Why is that? Well, because you know stuff that the computer doesn't know. You have common sense. But common sense is not a sense at all. It's a kind of knowledge. And that's key. So if I stand in front of this table and I block the edge, you can still see the edge starting here and ending over here. Why? Because you know about tables. The computer doesn't know about tables. The computer doesn't care about tables. So how does the computer know that there's an edge that starts here and ends here? It can't know unless you somehow inform the computer that it should somehow start here and end here and connect the dots. And the only way you can do that, the only way you can have a heuristic search that informs the computer that there are dots here and dots there and they should be somehow connected, is if you put the dots there. That informs the heuristic and allows the heuristic search to find a path somehow, however difficult, across the place where I'm standing and go behind and find an edge that connects those dots. And that's a key. Some people say, I don't know if this is true or not, some people say that's artificial intelligence. Okay. I'm here to tell you that over the last 30 years, if that's artificial intelligence is pathetic. Because 30 years ago, when I was working in the artificial intelligence industry, we were still doing this kind of thing. And in fact, the algorithm I'm citing here is probably more like 50 years old. So there's no reason why you should think of that as artificial intelligence. Maybe we could call it synthetic stupidity.
What do you consider artificial?
Well, this is a big question. That's a good question. What is artificial intelligence? I don't know. But it ain't that. Finding an edge where it was just looking behind you, but that's key. I mean, that's something that's, what is a good edge? Big question. Maybe it's not a valid question. And then the question becomes, what's a valid question? Which is a whole other question. That's a big question. So think about it in a different way. Okay, Hal, the computer who was evil, was supposed to be about 2001: A Space Odyssey. When did that program come out? Right? When did they make HAL 2001: A Space Odyssey? 1964, maybe? And we still don't have HAL, right? And in fact, now it's 2014. We still don't have HAL, and we're not even close. And in the last 30 years, we've made almost no progress, I say, in artificial intelligence, whatever that may be. Maybe you could call it machine vision or computer vision or pattern recognition.
Machine learning?
Well, learning. That's a great question. What is learning? I got a guy who was my office mate. He's now a program manager at Jet Propulsion Laboratory. His name is Rich Doyle. We correspond still. We were office mates in 1984. He worked with Patrick Henry Whitston, his advisor at MIT, on quantitative causal calculus. Basically, it says, Brian had a bad day, and Rich had a good day. Maybe Brian had a bad day because Rich had a good day. That's quantitative causal calculus. And you do all the permutations. The overflow on a bathtub makes the floor get wet. Maybe it's because you filled up the bathtub too much, and that's why the floor got wet. You want to call that machine learning? We never found out about what a container is. We never built the abstraction on containers, so we don't understand what bathtubs are. So if that's the case, if that's machine learning, I'm pissed off. I want my tuition money back. Because I took the course in artificial intelligence and all I could find out was Brian had a bad day because Rich had a good day. So it basically understood nothing. So what I'm thinking is, if that's machine learning, I'm pissed off. Where's the AI? There's no AI in that. So that's that, and that's the state of the art. 30 years later, Brian had a bad day because Rich had a good day. And that's machine learning. No kidding. Really. So, you tell me. Machine learning. Learning, yeah, what did we learn? We learned that there is no AI. That's what we learned. Now you tell me I'm wrong, and I'm happy to be wrong about that. Show me Hal, the robot. The only thing that comes close is IBM's Watson. And IBM's Watson does not scale into any other field. Not easily, anyway. They're trying to move it into the medical field, but it's just not working out very well for them. It's taken a very long time and a lot of resources. Maybe it'll happen, but it ain't Skynet yet. And humans versus the machines, the humans still win, okay? So, yes, sir.
Sorry, I didn't get that reference. What's Skynet?
Skynet. Don't you? John Connor, the Terminator?
Oh.
Arnold Schwarzenegger, governor of California? He was a great Terminator. What a great Terminator. He was. You don't watch movies? Oh. Sorry. Okay. Everybody asks me, what did you think of Arnold Schwarzenegger as the governor of California? And I say, what a great Terminator. So let's think about homogeneous point processing. What a fancy name for the simplest kind of image processing you can do. Take a function of a pixel and make a new pixel. We don't care about any pixels next to it. That's homogeneous point processing. You want to get really fancy? We call it isomorphic. Anybody know what that means? It's a math term. Yes, sir. No. Thank you. That's correct. You don't know what it means. It means one-to-one. It means it's analytic. It means it's the same forward as it is backwards. For example, an analytic statement in English. A bachelor is an unmarried male. What that means is that an unmarried male is also a bachelor. That's an isomorphic statement. One-to-one, it's true forward and backward. So isomorphic pixel processing says P prime equals f of P. If you can find f inverse, you'll be able to extract P from P prime. You'll find that term in linear algebra as well. So if we think that every point is treated the same, what we really mean is that no adjacent point has any impact on the point that you're dealing with. And so the size of the input image is the same size as the output image. We're not changing image shape. If we did, that would be morphological image processing, which means changing shape. It's great for doing statistics. For example, if you want to extract things like averages or standard deviation, you can claim that a pixel value is a random variable. When a pixel value is a random variable, then encountering different pixels must be a random process. If encountering different pixels is a random process, then we can extract all kinds of interesting probabilistic information about the random process. If we can compute the probability mass function, that is, the rate at which certain values occur, then that's the moral equivalent of the discontinuous version of a probability distribution function. If we can accumulate the probability mass function over different pixel values, then that's the moral equivalent of the continuous cumulative distribution function, only what we're really doing, instead of integrating a probability distribution function, is we're integrating a probability mass function with a summation. So all kinds of interesting statistics can arise from homogeneous point processing. And in fact, we'll make use of some of these statistics in this chapter. Typically, an image is a two-dimensional array. An image sequence would be a three-dimensional array. If you think about it, a transform of an input image f can give us a new image, and we can call it G. And that transform can take each one of the pixels as a function of x and y. And if we express that transform as a pixel array in 2 dimensions, then what you would expect is a 2-dimensional nested for loop. Doubly nested for loop will allow us to iterate through all possible pixels. Do you need to use a doubly nested for loop to iterate all possible pixels? No. You do not. Would it be more efficient not to? Yes, it might be. But we don't think of an image that way. We think of an image as a 2-dimensional array. But the image could just as well be a 1-dimensional array. And in fact, it often is when we get down into the application programmer interface that Java uses for representing the image. If you wanted to, you could use coordinate transform t sub x, which would be the x part, and then you could use t sub y as the y part, use the x and y coordinates on input, and then get new coordinates and then use those to feed forward our access into the image to get a new image. That's forward transforms. You can also do an inverse transform, where the coordinates come in from g sub x, y, and they're inverse transformed to give you the accessed image coordinates from the input image. There are advantages to doing an inverse transform. I'll talk a little bit about that later. So I'd like to try and create some sort of a function that will allow me to access the coordinates of the image in order to give me an output. And in this particular case, I got the square root of x and the square root plus the square root of r squared, and this is supposed to somehow give me a relation, right? This is an implicit representation of a sphere, right? X squared plus y squared equals r squared. We call that a relation. Why? It's not a function. How come it's not a function? Maybe I stop a second and say, hey, what's a function? You've heard of these things, right? What's a function? A function is when you get together. We're having a reception. Are we getting good reception? So what's a function? Yes, sir.
One variable in, you play with it, you spit it out.
You get one value out for every value in.
Yeah.
That's a function. If you have 2 values, possible values out, like plus or minus the square root of x squared plus r squared, then you have 2 values out. That's not a function. That's a relation. So if you think about the implicit representation of a sphere, it's a relation. The parametric representation of a sphere, the one that says you're creating the locus of points based on x equals r times cosine of theta and y equals r times the sine of theta, well then you have a single output for a given input. That's a parametric representation of the sphere. So parametric representations are substantially different from implicit representations. Right? We knew this from last week, maybe. So why do we need this? What's the motivation? And the answer is you can do brightening of the image. You can improve the contrast of the image. You can color the image. You can do a histogram equalization of the image in order to be able to improve the dynamic range on the image. You can convert to new color spaces. What's a color space? Anybody have any guesses? Yes, sir. A color space is defined by the primaries that are used to create the coordinate system. So, for example, red, green, and blue. Those are 3 different coordinates which can give you a color space. And all the points of color can be described within that space. Cyan, yellow, and magenta gives you a different color space. And the points in RGB can be moved or transformed into the new color space, cyan, yellow, and magenta. Hue, luminance, and saturation is a different color space. If you think about broadcast television, it's often described in terms of hue, luminance, and saturation to give you the different colors. So color spaces are basically linear systems that allow you to span all possible different colors using different coordinates. It's no more than and no less than a change of coordinates. And in some ways, it's a good motivation for learning linear algebra. So a color space is really just the, I'll call it Cartesian coordinates that are used to describe the different possible colors that you can encounter. That's a color space. Now, if you think about it, color spaces have inherent, I'll call it, advantages depending upon the application. For example, if you have a video projector like we have here, the color space red, green, and blue is actually very good for human color visual systems. But if you had something else like an inkjet printer, the color space cyan, yellow, and magenta is a great color space to use for painting with pigments on top of white paper. So at some level, one could make a claim there's an inherent advantage to using the cyan, yellow, and magenta color space for describing colored images when your intention is to print them. But if your intention is to display them, then you want red, green, and blue. If you combine equal parts of red, green, and blue, you get white. If you combine equal parts of cyan, yellow, and magenta, you get black. One color space is known as the RGB additive synthesis color space. The other color space is known as the CMY subtractive synthesis color space. Yes, sir?
So when we take like a negative of an image, is it changing the color space between those two?
No, you can stay within a color space and still do homogeneous point processing like negating an image. You can definitely, I'll say, leave the coordinates alone. So within that color space, you can do all kinds of homogeneous point processing. So change of coordinates is what you're getting when you're changing color space. Homogeneous point processing is different from a change in coordinates. So then comes the big question, how shall we implement the homogeneous point processing? And now my interface development senses are tingling. There are standards, and I've adopted these standards for doing homogeneous point processing, and what they do is they take R, G, and B inputs and they give you outputs. And if you have a nice interface that you're happy with, you can build an entire image processing framework on top of this interface, and all the different implementations for all the different interface implementation classes can be different. And this is an example of what we in the object-oriented programming community call polymorphism. So what does that mean to me? It means component software development. It means interchangeable parts. It means I can have code that can be reused in a framework that gives me a whole series of different operators that are within that family of image processing tools which we call homogeneous point processing tools. And those homogeneous point processing tools can be used with a wide variety of different graphic user interfaces. And here's the simplest possible transform of an image into a new image. And you can do this independent of X and Y location. And you could just take something like, well, I know f is a value, no matter what the x and y coordinate will be, that goes from 0 to 255. So let's write 255 minus whatever the value is. That'll give me the negation. For a grayscale image, it'll certainly serve to negate the image. Here's another one. We got x and y coordinates coming in with a, I'll call it, oh, thank you. Okay. A 24-bit pixel packed into a 32-bit quantity called an RGB quantity. And the RGB quantity is packed in there with 4 different values. The most significant 8 bits will be alpha. Then comes red. Then comes green. And then comes blue. They're all packed in using shift operations, which we studied earlier in the semester. So once these RGB packed pixels come in, you have to unpack them, do your homogeneous point processing, then you got to repack them and send them out the door as another int. So when you say filter RGB, what you're really doing is you're promising as part of the contract to grab out the red, green, and blue quantities, do what other kind of filtering you want to do, and pack them back in. Somebody, maybe Brian, asked, what do you need it for? And this is it. It was, yeah, I think it was you. You said, you know, how come we're learning about all of the shift and 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 exclusive OR operations? And will we be using this? And the answer is yes, here it is, in filter RGB. And you could see a whole lot of that. If I get out of the PowerPoint mode and go into the programming mode, I'll probably end up pissing you off and losing you all. But it's actually part of the reason why we had to study about the binary bit mask operations. Because you, in order to extract blue, what do? How do you take an integer with 32-bit quantity and the most significant bits are alpha and the least significant are blue? How do you grab out the least significant 8 bits from a 32-bit quantity? Do what now? You just AND it with FF. And then the least significant bits will fall right out. What if you want the least significant, instead of least significant 8 bits, you want the least significant 16, let's say 8 to 16 bits. So 8 bits starting at bit 8. What would you do? You want to get the green. How do you get the green out of this 24-bit packed pixel integer? Any ideas? Green is going to be bits, let's say 0 through 7 is the first, is the least significant 8 bits. So bits 8 through, what's the next one up? 16 is going to be the next 8 bits. So you want to get bits 8 through 16. How do you get those bits out of the int? Yeah, shift. Just shift to the right 8 bits, then mask with 0xFF, and now you've got green. And what if you want red? Most significant, well, it's not quite the most significant. Alpha is the most significant. Second to penultimate significant 8 bits. So that'll be 16 to 24 perhaps. You shift, right? Shift to the right 16 bits and then AND with 0xFF and blammo, you've got red. So if you're going to be packing everything into 32 bits, you're making a statement about the computer architecture of the underlying machine, aren't you? You're saying, hey, wait a minute, that machine must be a 32-bit machine. Well, that's a safe bet for a Java virtual machine. Java virtual machines are all RISC machines, and they're all 32-bit machines. So handling 32 bits at a time makes perfect sense. and doing the packing and unpacking inside of the CPU so that you can do your homogeneous point processing, that makes perfect sense. And it's very efficient. So here it is. Here's your packing junk. The packing junk. Right? Bits for B are computed by, let's see if I can get an arrow here. Oh, there we go. See, here's B. There's the RGB, that's the 32-bit quantity. We AND it with 0xFF, and there's the B part. Take the RGB, AND it with 0xFF with 00, shift it to the right, and now you got the G part. Now you can get the red part similarly, and you can see the FF is moving over by 8 bits at a time so that you can get alpha, red, green, and blue. That's how you do homogeneous point processing. This color at the top, this says 7F, which is equal to the decimal quantity 127. And then there's some color, dead 50. It's hexadecimal, it spells stuff. So the least significant value, least significant 8 bits, will be 50. The next, that's the red part. The green part is going to be AD, the red part will be DE, and alpha will be 7F. That's key. Once I've got red, green, and blue, I can do other stuff, whatever that may be. What will red, green, and blue do for me? I don't know. They'll take those colors and they'll do homogeneous point processing. Not only independent of the location of the pixel, but even independent of the adjacent colors, red, green, and blue. And then at the end of the day, once you have red, green, and blue, what do? You pack the pixel again. So now you take the red and the green and the blue and you shift them to the left, and you inclusive OR, right? That's different than bar, is single bar, where single bar is an inclusive OR, bar, that's a Boolean OR. And then you proceed to pack the pixel and return it. So you're doing an unpack and a process and then a repack. How's that grab you? You got that, Rich? Where did Rhodey go? Rhodey, you still there? You awake, Rhodey?
I'm looking at your screen.
Okay. Does it make sense already? I can't see your face. There's computers in the way. Does it look all right? Yes, sort of. It's not kind of a yes. Tell me what part of this code confuses you.
Let's see. I guess just that.
Which part?
That first, or the RGB.
I just made up some sort of value for the
Okay.
RGB quantity.
Then I'm good.
Okay. So here's my interface. Sometimes I think that in life as well as in programming, the simplest interface is the best. This is the simplest interface I could come up with. I really hate clever code, and I'm hoping this code doesn't strike you as clever. But the goal is you take a red, green, or blue value, you pass in some function that you have to implement, which will be the implementer of the homogeneous point processor filter interface, and then it will give you red, green, and blue out. If you can implement that interface, then you can devise operators that will plug into my framework. And that's the goal, right? You want to be able to have component software development because that gives you the interchangeable parts of software engineering. Let's see if we can find some homogeneous point processor interface implementations. Wouldn't that be swell? So for image interfaces, I've got a couple of interfaces. Here's one called the image processor interface. And remember what I said, the simplest possible interface is the best. Here it is, the simplest possible interface I could think of for image processor operators. An image goes in and an image comes out. I don't know how you're going to implement it, and that's where the polymorphism comes from. So this could be arbitrarily complicated. Garbage in, garbage out. Data processing, only it's data processing with an image. Hence the term image processing. Now let's take a look at the image processor interface implementations in the form of a homogeneous point processor interface. And I got a whole package for that. And here's the homogeneous point processor interface called the HPP filter interface. And it takes a red, green, and blue quantity in and passes a red, green, and blue quantity out. With this one interface, I can implement Chapter 4, which allows me to take images, pipe their pixels into some function that you may have devised on your own, and then get a new image on the output. How's that grab you? Seems trivial, right? And what good could this possibly do? Does this have any impact at all on my code? Does this get used anywhere? Let's find the usages. Well, there's 27 usages of this one interface. How about that? The homogeneous point processor interface. So here's something called the pseudo-color filter. Pseudo-color filter. What's a pseudo-color? What's pseudo-color mean? Pseudo. What's pseudo mean? Yeah, false. False color. So the false color filter takes all the colors and maps them into different colors. So it makes colored images. Cool, right? And now what we'd like to do is take a look at how we implemented the pseudo-color interface. Remember, the homogeneous point processor interface requires that we have the ability to take red, green, and blue values and map them into new values. Well, here we're doing that. We're doing just that. Only we're getting some function, and in fact, it's the same function for each red, green, and blue. Same function. So whatever red, green, and blue values are coming in, we use different function parameters, but in effect, when we go to get the function, we're doing a reasonably simple operation, a sign or whatever it is we're doing in here, and getting new values coming out. The pseudo-color filter. Where's that get used? I got lost. Pseudo-color. P-S-U-D-O. Yeah, here it is. Colorize. So we take the pseudo-color filter, we pass it into this thing called the homogeneous point processor filter image processor. Wow, what's that do? Let's have a looky-loo. It implements the image processor interface. It takes the homogeneous point processor filter interface. It applies it to red, green, and blue for all the different pixels and creates what's called a color lookup table. Color lookup table. What could that possibly mean? It's a color palette. So for every color used on input, we should have a different color on output. So once we establish the color lookup table, what that means is no matter how complex it was to compute the color lookup table, all we need to do is take a color on input and we'll be able to get a color on output just by looking it up. How cool is that? Because what we've really done is we've traded space for time. Right? Space for time. What that means is you can make an arbitrarily complicated function to create the color lookup table. And it could take as long to compute as you want. But once you have the color lookup table computed, all you have to do is grab the color pixel, put it into the lookup table, and you'll find the new color. Right? And it will happen at the rate of memory access, not the rate of some computation of a variety of transcendental functions. So that's a big win. Right? Computationally, it's fast. And how much space will that consume? How much space does it take to store a color lookup table? That's a good question, right? Because if it takes up a lot of space, that's a big problem. So then the first question will be, well, wait a minute, how many colors are there? Anybody know? Infinite. Infinite colors. Who thinks there's less than infinite colors? In theory, there should be infinite colors, but in practice there isn't, because the computer is storing 8 bits per color, and there's only red, green, and blue, which gives us a grand total of 24 bits, which means the grand total number of different colors is 2 to the 24, which is 16 million different colors, and that's it. And that's it. 24-bit direct color images have 16 million different colors and no more. Huh? They can have less. They can certainly have less, but they have no more. Distinct, different colors. And a lot of times pixels in an image number less than 16 million. As a matter of fact, it's perfectly reasonable to have an image with 1 million pixels, or even 500,000 pixels. And as a result, it couldn't possibly have 16 million colors. Right? Because how can an image with 1 million pixels have more than 1 million different colors? And as a matter of fact, it would almost certainly have less than 1 million different colors. The only way it would have 1 million different colors is if every pixel was a completely different color from every other pixel, which almost never happens, because we have a lot of interpixel coherence within an image, large areas of constant color. So 16 million colors, that's a lot of colors, but 16 million, it ain't infinity, right? It's less than infinity. And if you had to have 16 megabytes, that's nothing. Really nothing, right? 16 megabytes. Here in the new age, where we have gigabytes of memory, 16 megabytes is nothing. Yes, sir?
Could you talk about the size of pixels? Because I'm a little confused sometimes when, like the physical size of a pixel, I don't know.
A picture element.
Yeah.
Oh, it's often abbreviated in the term PEL. P-E-L for picture element. A pixel is a picture element. And the question is, what is the size physically? And that depends on the display. If you have a display like a Mac Plus from 1984, there were 72 binary pixels per inch. And they did that because there were 72 picas per inch in typography. And so that would be the pixel density in the display. Here in the new age, people use color. And with color pixels, it's typical to find something on the order of 72 color pixels per inch or 92 color pixels per inch on a display. Well, if you're thinking about print, it's different. If you're thinking about print on paper that's absorbent, it's different than if you think about print on 60-pound gloss. All right? Why? Because 60-pound gloss, which you see on the tip-ins of the image processing in Java book, will give you 155 lines per inch, where each line has a line of pixels. And that's because it's being printed on glossy paper. Glossy paper is different from regular paper because glossy paper does not absorb ink. When ink gets absorbed, it spreads out. And that spreading is known as dot gain. And dot gain is minimized with glossy paper. When the paper is not glossy, the dot gain increases. When you look at a copy of USA Today and you look at the front page, which is often in color, you'll see an 83 line per inch screen because newsprint has really terrible dot gain. Newsprint has so much dot gain that when you look at the paper, it looks out of focus because the color doesn't look really very good. But when you look at the tip-ins on my book or on some reasonably high-quality magazine like Cosmopolitan, you'll see they're using 60-pound gloss, and it's very much a heavy paper which has been coated, and it's been used with what's known as an image setter. The image setter will take 2,540 dots per inch for cyan, yellow, magenta, and black, and they will create a translucent, I'll call it film. And the film has a high opacity black. And then that is used to expose a copper plate. And the copper plate is then used as part of the printing process. That's how printing works. That's why printing has an economy of scale. Economy of scale means that if you print a lot, it's cheaper per unit than if you print a little. So what you want to do when you run a book like this is you want to print 5,000 units. If you're not going to print 5,000 units, forget about it. Because you're not going to be able to get the costs down on a per unit basis because of the cost of plates and the cost of setting up a 4-color printing press. They call it 4 colors. One of the colors is black. The other 3 are cyan, yellow, and magenta. So when you think about the size of a pixel, you have to think about it in the context of your process for display. You either have a display process like a computer display, like this laptop or that overhead projector, or you have a print process like a laser printer or an image setter. Yes, sir?
If I generate an image with a higher pixel density per inch and display it on a display that is a lower density, does that make sense what I'm saying?
Say it again.
So I generate an image with a specific pixel density, and then I display that image on a display that has a lower pixel density than the image's pixel density. Does that make sense?
Okay, an image has a certain number of pixels.
Yeah.
The number of pixels in an image is independent of the number of pixels in the display. It's also independent of the number of pixels per square area in the display, which is what you might call pixel density. So the number of pixels in the image doesn't change. So if you give me 1,000,000 pixels and you tell me you want me to display 1,000,000 pixels, let's say, on a page, and the 1,000,000 pixels is, I know, equally adjusted for both height and width, so it's almost a square image, or it fits in the aspect ratio of the page, then I've got to take your image and somehow squeeze it down into the page. Now, it may be the case that the page has more capacity than the number of pixels in your image, in which case I may duplicate the pixels and scale the image. Or it may be the case that the number of pixels in the display on this page is fewer in terms of its density than the number of pixels in your image. And if that's the case, then I'm going to have to lose a few pixels by decimation, by sampling the image or resampling the image so that I only get every other pixel, for example, and that'll allow me to reduce the pixel count and size.
That makes sense. This brought up another question of mine. So if I stretch an image, for example, I'm increasing the size of all the pixels equally.
If you want to devise an algorithm whereby you increase the size of the image by increasing the total number of pixels, you can certainly do that. And if you're asking if you can devise an algorithm that would allow you to maintain the aspect ratio, the answer is yes, you can. And if your next question is, can I devise that algorithm so that it allows me to maintain the aspect ratio and make it so that the number of pixels increases uniformly for X and Y, you can do that too. So you could double the number of pixels in X, and you could double the number of pixels in Y just by replication. That's a simple algorithm, but it would work. And it would certainly allow you to maintain aspect ratio, double the number of pixels in the image, and effectively double the number of bytes you would need to store the image. The question of whether or not that's a good algorithm for anything in particular is another matter. I don't know if you'd want that algorithm.
No, it's coming together.
Yeah. So the number of pixels and pixel density are completely different things. One refers to the actual data structure, the other refers to the display. An image instance has no notion of its pixel density in general. It's just a data structure that stores pixels. It's a pixel container. That's it. The question of what you want to do for display, that's another matter. I don't know if that made any sense. So now the question is, what do you need for a lookup table? If you look at what you see here, you need 3 channels, red, green, and blue. And then because there are 256 different possible values, you really only need 3 times 256, or whatever that comes out to be, different possible bytes. In my case, I'm using shorts to store everything because it's convenient. And so that's a relatively small quantity. In fact, if you looked at this lookup table, it would be something on the order of 3 times, oops, I wrote S, 3 times 256 times, in my case, 8 bits per short, no, 16 bits per short. So 2 bytes. So 2 times 256 is 512. I'm thinking 756 bytes total. And that's your space for time trade-off. And you use that lookup table, you do your search. Instead of searching 16 million colors, you search the red lookup table, the green lookup table, and the blue lookup table separately. And then that gives you the ability to get, well, essentially 256 different possible colors for your 16 million input colors. And that's a very efficient way to allocate memory for a lookup table.
Sorry, where's the 2 come from?
2 bytes per short. A short is 16 bits. So I'm thinking that, I don't know, what are they, don't they have like calculators in Windows? Calculators. It's a computer. It should know how to calculate things, shouldn't it? So 2 times 3, I think that's 6, right? Oh, good. Times 256 is equal to 1,536 bytes total. Now, if you did it only in terms of number of shorts, divide by 2, and you'd get 768 shorts. So that's the total number of shorts needed in the lookup table that's going to produce 256 colors in a pseudo-colored image. And that's it. Yes, sir?
I have some more challenging questions. So we're using 8 bytes for each red, blue, and green, right? So
Yep.
256 possibilities.
Yep.
Why are we using 8 bytes and not something like 16 bytes?
Okay, great question. Turns out when you're dealing with direct color images in the Java AWT API, you're dealing with 24-bit color images. And that's just the way they set up the API. But if you told me that you were working for the Jet Propulsion Laboratory on the Hubble Space Telescope, I'd tell you 8 bits ain't sufficient. That for any celestial telescope, you probably want 16 or 24 bits per channel. And it wouldn't be red, green, and blue, because some of those scopes are outfitted for ultraviolet and X-ray and infrared. And all those things are going to be very sensitive sensors, and they're going to have enormous dynamic range. And once you pseudo-color those, you'll be able to visualize what comes back, but then you'll say, what does an X-ray look like? And you're going to need to pseudo-color it, because otherwise humans won't be able to visualize the X-ray image's intensity, because humans don't normally see X-rays. But X-rays are such an important part of what comes back from celestial bodies, especially when you're dealing with supernova and other interesting phenomenon that you might be studying. So as I see it, you're really going to have to worry about what it is you do to do scientific visualization for high dynamic range sensors. Your screen, on the other hand, is a direct color screen. And your screen, your display, is only going to do 24 bits per pixel. So now you've got a big question. How do you map those high dynamic range images and sensor information into 24-bit quantities? This is a big problem. I was thinking it would be really fun to go and get the MRI of my knee, which I had done recently because I had some knee injury earlier this year. And I thought, biomedical visualization, let's give it to the students. We can all look at my knee. Well, it turns out they have a process which we call here in the New Age tomography. Tomography has changed the way biomedical imaging has resulted. Does anybody know what tomography means? Have you never heard of tomography? Have you never heard of a CAT scan? What is a CAT scan? In 3D, right? It's tomography. You're taking slices, and the slices of the image are going to give you different intensities, and what you get is a constructive solid geometry in the form of a volumetric profile. And this enables you to do a kind of biomedical visualization, right? How cool is that? Look at, for example, Hologic, a company based in Danbury that has shipped 5,000 3D digital mammography systems. Right out of here in Danbury. Real manufacturing in Connecticut. What are they doing? They're doing tomography. They're taking slices of breast tissue looking for cancer. This is like having serious societal impact because this is killing people. And so they're able to visualize with high resolution small tumors, like millimeter and submillimeter tumors, prior to their becoming metastasized, which will kill people and at a high rate. So this is one of those things where if you can find these things and excise them or treat them rapidly, you can save a lot of lives, right? What's the big killer in this country? Right? It's either cancer or it's heart disease. And right now it's cancer, right? It used to be heart disease, and they trade off with one another. And what's the big cancer killer in this country? Smoking. There's lung cancer. And what's the other one? Second biggest cancer killer?
Heart cancer.
Heart cancer.
I mean heart disease and then
Brain cancer. Breast cancer. What kind? Colon cancer. Yes, bingo. 150,000 new cases per year. Colorectal cancer. Why? Why? It's the grill, right? The grill, when you cook meats on the grill, it creates blue smoke and it causes a cracking of the grease. It breaks down and becomes a carcinogen. It's the grill. Everybody, I don't know if you've ever had anything off the grill. If it's burgers, it tastes like burgers. If it's, omelets, it tastes like burgers. Right? Everything tastes like burgers. Yes?
Just to clarify, are you talking about propane, charcoal, or both?
Oh, this is a high heat cooking surface on top of which everything goes. The bacon, the pancakes, the hamburgers, the chicken, right? Makes your omelets taste just like chicken. Vegetarians love it when the omelets taste like chicken. So, as it happens, it's okay to eat the chicken embryos, but nobody wants to eat the chicken if they're a vegetarian. Right? You say, but poor chicken embryos can't run away. Yeah, but they don't have legs, therefore it's okay to eat them. It's true. Unless you're an ovo-lacto vegetarian, you're cool with eating eggs, which are nothing more than unborn chickens. But you're not cool with eating chickens. Right?
Well, I can think of a lot of arguments against that.
It doesn't have to make sense. This is just the way it is. I'm a vegetarian, been that way since the 70s. And I'm here to tell you, you can eat chicken embryos, but you don't eat chicken. I eat eggs. We don't call them chicken embryos. Okay? We don't. It's not correct to call them chicken embryos. Oh, poor little chicken embryos. Oh, you're helpless. So it turns out, right? You can eat you can eat eggs. You don't eat chicken. That's what vegetarians do, right?
I guess. Wait,
Yeah.
Back to the grilling and the cancer.
So back to the grilling and the cancer. All of that stuff gets cooked on the same grill, and when you go past the Burger King, you can see the smoke coming out is blue smoke. That's the cracking, the molecular cracking of the grease and turning it into a carcinogen. And that's where all the colorectal cancers are coming from. But nobody bans that junk. So as it happens, we, perhaps as Americans, have a very poor diet. And I think it's a contagious one because the Chinese and the Japanese are all figuring out that they like McDonald's too. And so then what happens is the rates of colorectal cancers increase. Now the question of, why people haven't stopped it is another matter. I think people are beginning to figure this out because the sales at McDonald's are declining. People are figuring out that, this is not good for you. But as it happens, that's where you're getting that high incidence of cancer. And how do you stop the high incidence of colorectal cancer, which is an extraordinarily small rate of spreading? And the answer is early detection. And the detection is done through imaging. And the gold standard for imaging in colorectal cancer is a colonoscope, which is a real right-up-your-ass procedure. Literally, I'm here to tell you. And so there are other ways to do that kind of imaging. One way is a CAT scan. Instead of putting a machine in the body, which is a little invasive, you can put the body in the machine, which is considered not invasive. Right? An aspirin is invasive because you're putting something in your body. Right? A bandage is not invasive because you're putting it on your body. Go figure. So as it happens, if you do a body in the machine where you do a virtual colonoscopy, which is a tomographic process that does virtual slices through the body, it's considered non-invasive. And you can do things like find cancer. It's not FDA approved and insurance won't pay for it, but it allows you to avoid the dreaded colonoscopy, which you will all have to do eventually. When you get to be 40 or 50, yeah. They'll tell you to do that. Yeah. It's just the fact of life. It's one of those things. So, when you do this lookup table thing, what you're really trying to do is take those aspects of the image which weren't particularly evident and make them dramatically evident. So if you said to me, gee, here's something that just looks like a shadow and I don't really see it, I as a surgeon might miss that. I as a radiologist who's looking for cancer might miss that. But if I did pseudocolor and I colored in those things which are the tumors that I'm looking for, well, that allows me to say, hey, wait a minute, that's something I should look at. That's very important. So there are these things that people do in order to be able to take the tumors to determine if they're cancer. They excise the tumors from the body and they do an examination of the tumors, and that's a process known as histopathology. But if you are able to do it without excising the tumor then that's known as in vivo histopathology, where in vivo histopathology means you're doing it inside of the living body. And to visualize the tumor and detect the tumor or diseased tissue inside of the living body, you can use a number of different techniques. One way is staining. Right? People use all kinds of interesting dyes, radioactive dyes, some dangerous stuff that you may have to drink in order to be able to see better those things that you're looking for, like endometriosis or different kinds of cancer. Another way to do it is different kinds of light. Lasers have very narrow bandwidths, a couple or 3 nanometers for their bandwidth. Well, it turns out if you take a Blu-ray laser, which runs around 400 nanometers, plus or minus 3 nanometers, and you shine it on something like endometriosis, it fluoresces. And it says, yes, hi, I'm diseased tissue. And you can see it in a way that the surgeon wouldn't otherwise be able to see. They call that laser-induced autofluorescence. You don't need to have any kind of chemistry staining the diseased tissue in order to be able to see it. So that's key. Being able to see that diseased tissue, having it pop out and say, hi, here I am, that's key to being able to do an early diagnostic process on the diseased tissue. This is the kind of stuff that saves a lot of lives. Remember, second biggest cancer killer in the country, colorectal cancer. And yes, those polyps, which are cancer, say hello when you shine a Blu-ray laser on them. So that's laser-induced autofluorescence. And it's not widely used in endoscopy, and as a result, almost half of the polyps are missed. And that kills people, big time. Because when those polyps are missed, the people die of colorectal cancer. So how do you keep people from missing the polyps? Lookup tables. Yes, lookup tables. That's what you use. And with the lookup tables, you should be able to colorize images. What a good thing, right? Colorize the images. So to colorize an image, I've got these image utils. Colorize. Oops. Colorize. Yep, there it is. So now you can take an image, go in, pass in double precision numbers, red, green, and blue, and modify the image with a pseudo-color filter and homogeneous point processing, and this will give you a new image. And I thought it would be fun. Wouldn't it be fun if we used colorize and image utils with a wide variety of red, green, and blue quantities in order to be able to, see how all that stuff works. And it says no usage is found, so this is a great opportunity for us to write a simple example. So let's do a colorize example where we colorize an image. And what we'll do here is we'll make a new image, Java class file, and we'll call it the colorize example. And for my little example, what I'll do first is I'll get an image, and then I'll display the image. Image utils dot display image, and we'll give it a name. And I believe display image is required, image. And something's wrong. It doesn't know about what an image is. Oh, and we need a main, public static void main, Control J, enter, and take these things and put them into the main to make a nice main. I knew I was forgetting something. And then Alt enter to import the image. And this should allow me to open and display an image, which we've seen before. Let's find a nice image. Beg your pardon?
This is in J2D.
Yes, it's in J2D image utils. Here's Dr. DeFracto. Oh, that's a scary one. All right, let's not look at that. So now what we'll do is we'll go to image utils, and then we'll colorize the image. And then this is a classic example of homogeneous point processing. And it says here I need 3 numbers. Let's pick numbers between 0 and 1. 0.1, 0.5, I'm making up numbers, 0.6, and then we got to put in the image. Oh, I think I need a comma here. 0.6, and then put in an image, and that'll give me a headache because it doesn't work. What's the problem here? Oh, I got a point after the 5. There's a little typo. That's better. And the output should be a new image. Let's call it image img2. And now we'll display that image. Image utils.displayImage. It's my first example of homogeneous point processing using colorization and a pseudo-color image. How exciting. And the output will be img2, and we'll give it the name img2 because I lack imagination. And let's see if this works. What could this possibly do? Dr. DeFracto. And there it is, a colorized image. Homogeneous point processing. Nice and fast. You want to see the code again?
Yeah, I just want to make sure I have it.
There it is. Homogeneous point processing. Colorization of an image. And so that's, one of the things you can do with homogeneous point processing. Other things you can do, which we can discuss later, includes histogram equalization, adjusting brightness, adjusting contrast, doing adaptive, non-uniform, histogram equalization, or doing uniform, non-adaptive histogram equalization. And we'll talk a little bit about those two things after the break.
What's the 0.1, 0.5?
Oh, yeah, where do these numbers come from? Anybody know? I made them up.
What do they do?
Well, they're adjusting the sine wave that I'm using for the red, green, and blue lookup table composition. So what I did was I decided to parameterize how the lookup table would be formulated. In this case, I'll do the same lookup table for everything. Red, green, and blue will run the same, and we'll see if that looks different. Here's the girl. Now it looks quite a bit different. So how's that grab you? You could put in any numbers you like. Typically I use numbers between 0 and 1. Here's the baboon, and there he is after the pseudo-color. How's that? Fun, right? Very psychedelic. It's like the 60s here. You guys don't remember the 60s because you weren't alive then.
Mine's not.
Yours isn't doing that?
I get out of memory.
Out of memory? Really?
Maybe the image I picked isn't.
Maybe pick a smaller image.
How do I get a small?
Well, I have a whole bunch of them. Did you try the baboon?
Wow, no.
Oh, you don't have my images. Well, I don't have your images either, so that's fair. When I distributed all.jar, it contained a data directory.
Oh.
Yeah, and the data directory contains a whole bunch of data, which includes images.
there was food in the engineering office?
Oh, yeah, if you guys want to go head out and grab a snack, let's do a pause and go into the engineering office and see if there's any food left. I think